All right, happy Tuesday, everybody. So we're into our second full week of e-learning, and then we also have 5 more weeks left in the school year. I made this announcement, and I think there was an email sent out too, but the schedule for the rest of the school year has changed a little bit. I've updated that syllabus and that calendar so you can take a look at it. We're also not going to be doing final exams this year. We're still a little bit unsure how we are going to be doing grading and how we're going to be assigning credit. Your safest bet is to do all of the assignments that your teachers are posting. And then you'll get credit probably regardless. But we're still working out how that credit's going to be assigned. But it won't be through final exams. Okay, so what are we doing today? What is our lecture for today? We're going to talk about this chemistry concept called the mole. The mole. So, the mole is a really, really important concept in chemistry. And it's not those things on your face, it's not the little mammals that dig in the ground, separate thing. In chemistry, a mole is a unit of measurement. It is a unit of measurement, like a milliliter, or a pound, or a kilogram. It's something that we use to measure other things. The mole, this idea of the mole, it originally came around because of this guy. His name was Amadeus Avogadro. Amadeus Avogadro. So Amadeus, he originally came up with this concept when he was studying the behavior of gases. And he said that if 2 gases are at equal temperature, pressure, and volume, then they will have the same number of particles. If 2 gases are at the same pressure, temperature, volume, then they're also going to have the same number of particles. And that is Avogadro's law. Like most things in science, at first, people didn't believe him. They might have laughed at him a little bit. It was not for another 40 or 50 years that this idea started to catch on, this relationship between gases. And then it was even expanded further into this concept of the mole. So, I told you it's like a unit. It is a unit of measurement. It's like a counting unit, like a dozen. 1 dozen of something means 12 of that thing. If I had a dozen roses, I have 12 roses. 1 mole of something is 6.022 times 10 to the 23rd of that thing. So I'm going to go over that again. MOL, this is just our abbreviation for mole. If it's MOL, we know it's a unit, and it's not that little digging critter. So MOL, mole. 1 mole is a really big number of something. It's 6.022 times 10 to the 23rd of that thing. That's much, much more than a trillion, more than a quadrillion. It's a huge number of things. But again, it works just like a dozen does. If I have a dozen puppies, I have 12 puppies. If I have a mole of puppies, I've got 6.022 times 10 to the 23rd puppies. A lot of puppies. So it's just a counting unit. It's a very big counting unit. If I say that I have 1 mole of something, this is how much I have. 6.022 times 10 to the 23rd of that thing. Let's take a look at some examples. I've actually got some moles here with me now. So I've got 2 examples of moles right here. I've got a mole of water and a mole of sugar. And you can see that these are pretty different in their amounts. A mole of water doesn't seem like a lot of water, but a mole of sugar, that looks like quite a bit of sugar there. But I'm telling you, both of these are 1 mole. 1 mole. That means that there's 6.022 times 10 to the 23rd molecules in each one of these. 6.022 times 10 to the 23rd molecules of water, 6.022 times 10 to the 23rd molecules of sugar. So if I'm telling you that it's the same number of molecules, and it is, it's the same number of molecules, roughly, in these two glasses, why does it look like there's so much more sugar compared to the water? It's the same number of molecules in both. So why does the sugar look like it's so much more? It has to do with the actual size of the molecules. So if we do a comparison of these moles here, a molecule of water is relatively small. It's got 1 oxygen atom and 2 hydrogen atoms, and that's 1 molecule. We said that this little glass over here has 6.022 times 10 to the 23rd of this molecule right here. But then if we look over here at sugar, this is a molecule of sugar. Sugar molecules are much bigger than water molecules. I've got 6 carbons, 12 hydrogens, and 6 oxygens, all in 1 molecule. And then I've got 6.022 times 10 to the 23rd of these molecules. That's why it looks like the sugar is so much more. It's just because the individual molecules are bigger. So when I compound them on top of each other, the mole gets much bigger too. This is a little bit of a look ahead for tomorrow's lecture, but we're going to learn how to do something called the molar mass. It's the mass of 1 mole. So the molar mass of water is 18 grams per mole. That means that in 1 mole of water, there are 18 grams. That's how I was able to measure out this mole. I did 18 grams of water, and I put it in this glass. 18 grams, that's 1 mole. That's why I knew that this was a mole. The molar mass of sugar, of glucose specifically, is 180 grams per mole. 180 grams in 1 mole of sugar. So we're seeing that a mole of sugar is about 10 times as massive as a mole of water. And that's because the actual molecules are about 10 times the size of water. So the way that I measured out this mole of sugar is that I measured 180 grams, and if I know that 180 grams is a mole, then I know that this is a mole too. Hopefully you're seeing why the mole is helpful. I could try and sit and count all the molecules, 1 molecule, 2, 3, 4, 5, all the way up to 6.022 times 10 to the 23rd. It would take my entire lifetime, and I probably still wouldn't make it. So counting the individual molecules is not worth anybody's time. Instead of counting the individual molecules, we count the moles. It's much, much easier to measure out 18 grams or 180 grams as opposed to getting a microscope and counting all the molecules until you get up to 6.022 times 10 to the 23rd. So the mole, it is a unit. It's a unit that's based off of a number, like a dozen. A dozen is 12, a mole is 6.022 times 10 to the 23rd. So we can see that not every mole is going to look the same. We did the example of a mole of water and a mole of sugar, and they don't look the same. They look like they're different amounts. That's actually because of the size of the molecules. The number of molecules is the same. It's just like if you had, let's say you had a dozen golf balls, 12 golf balls. And then you've also got a dozen basketballs. A dozen basketballs is going to look a lot bigger than a dozen golf balls. It doesn't change the fact that there's 12 of each. Same thing here. A mole of sugar looks like a lot more sugar than a mole of water. It doesn't mean that there's not the same amount in here. There's 1 mole in both of these, but the things that I'm counting are different sizes, just like a golf ball and a basketball. So how are we actually going to use this concept? How can we apply this to what we've already learned? We're going to do some dimensional analysis, and I'm sure that you're excited about that. We'll do maybe 3 or 4 examples on the whiteboard here, and then we'll wrap it up for today. You actually only have 1 homework assignment for this whole week, and I'm making that homework assignment due on Thursday night. So you kind of get a little bit of a break from homework here for a while. So we'll do these 3 or 4 examples, and then we'll wrap it up for today. Let's do it. So we learned what a mole is. Now let's talk about how can we apply this to what we've already learned. What are the problems going to look like when I ask you to do problems with moles? So we're going to do one together. Hopefully everybody can read this whiteboard here. But what my problem says, it says, how many atoms of titanium are in 0.25 moles of titanium? I'm going to use all of my good story problem strategies. So I'm going to follow the question word. How? How many atoms? I know that my answer is going to be some number of atoms. Maybe it's 5 atoms. Maybe it's 1,000,000 atoms. I don't know. I'm going to find out. So how many atoms of titanium are in 0.25 moles of titanium? The way that I'm going to solve this, I'm going to have to use dimensional analysis. This is why we've been practicing dimensional analysis this year. Hopefully we're still good at that. You might have to brush yourself up on it. That's fine too. When I'm doing these dimensional analysis problems, I always like to start by following the question word, like I said. How many atoms? This is the unit that I'm going to start with, atoms. So I will put atoms in the numerator, and I'm saving myself lots of space here. Now, what unit am I comparing that to? I know that atoms are in the numerator. What should I put in the denominator? This is where I'm going to put my moles. M-O-L, mole. So I'm doing a comparison here. How many atoms are in 1 mole? This is actually something that we learned just earlier in the video. Remember that I told you 1 mole is 6.022 times 10 to the 23rd power. I'll give you a little close-up here. 6.022 times 10 to the 23rd atoms in 1 mole. It's a counting piece. It's just like a dozen. If this was 1 dozen, I would put 12 atoms, but it's a mole. 1 mole is 6.022 times 10 to the 23rd atoms. My problem's not done yet though. I still have not used this number from the story problem. So I'm going to set up a new fraction. I'm going to take this unit that was in the denominator and I'm going to carry it up. Moles. I'll search my story problem for something that has moles in it. I've got it right here. 0.25 moles. I don't want to know how many atoms are in 1 mole. I want to know how many atoms are in 0.25 moles. I can put this one over 1. So here's my setup. I'm ready to solve now. These units cancel out, my moles. So the only unit I'm left with is atoms. But that's good, because that's what the question is asking me for. How many atoms? I would do Avogadro's number, 6.022 times 10 to the 23rd, times 0.25. And my answer, with significant figures, would be 1.506 times 10 to the 23rd atoms. I could even put of titanium. So I realize that's a little bit hard to read over there. I kind of ran out of space. But here is my setup. I started with the unit that followed the question word. How many atoms? Atoms. I compared that to moles, and I said that there are 6.022 times 10 to the 23rd atoms in 1 mole. But I'm not looking for 1 mole, I'm looking for 0.25 moles. So I set that up as my second fraction. I multiplied across, and I managed to get this answer. 1.506 times 10 to the 23rd atoms of titanium. That's still quite a lot of titanium atoms. And that's just because the mole is such a huge number. Even if I am only taking a quarter of a mole, it's still a ridiculously huge number. Let's try 2 more problems. We'll do 2 more problems on another board, and then we'll call it there. Alright, here we go. Alright, so we got 2 more examples to wrap up the video for today. I actually just had a Zoom meeting in the middle of filming this lecture. Grades are going to change again. We just got new word from administration that's going to change the way that we do grades one more time, hopefully for the last time. So keep an eye on Skyward. You're going to see some big changes, all positive for you. These are all good changes for you. So definitely keep an eye out there. Let's take a look at these last 2 problems to wrap up our video for this week. So we'll do these one at a time here. I also want to point out a little abbreviation that I use. Excuse me. So in the corner up here, I put a little abbreviation that you can use that might make your life a little bit easier. Avogadro's number. Remember, Avogadro's number is that really big number, 6.022 times 10 to the 23rd power. Instead of writing all that out, we can abbreviate that to N sub A. N sub A, number Avogadro. So I'm going to do that just to save myself a little bit of space here. Anywhere I put NA, that is Avogadro's number, 6.022 times 10 to the 23rd. So, starting with this top problem. How many viruses are in 2.6 moles of viruses? Let's follow the question word. How? How many viruses? So I'm going to start with viruses in my numerator. I'm trying to get to moles. I know that 1 mole of anything is Avogadro's number. Avogadro's number of viruses are in 1 mole. But I don't have 1 mole, I have 2.6 moles. My units cancel out, just like the last problem that we did. I'm going to do Avogadro's number times 2.6. So my answer, I don't have a calculator handy, but my answer would be 2.6 times Avogadro's number. That many viruses in 2.6 moles of viruses. So you're seeing that I'm doing my dimensional analysis to cancel out my units until I only have the unit that I want, and then I multiply the numerators and the denominators. Let's do one more. This last one, I switched up the wording a little bit. The problem is essentially still the same. How many moles are in 4.5 times 10 to the 19th Skittles? It's a lot of Skittles. Follow the question word. How? How many moles? This time, I'm going to put moles in the numerator. And in the denominator, I'm going to put Skittles. I know that 1 mole of Skittle is Avogadro's number of Skittles. Remember that Na, Avogadro's number. So 1 mole of Skittles is this many Skittles. But I don't have that many. I've got a specific amount of Skittles. So I take this unit, I carry it up, Skittles. And I'm going to put this number in here. 4.5 times 10 to the 19th. I can put this one over. So the work is pretty much the same. This unit cancels out. The only unit I have left is moles this time. The difference is, instead of multiplying this time, my answer would be 4.5 times 10 to the 19th divided by Avogadro's number. So because this number was in the numerator and Avogadro's number was in the denominator, my answer is just going to be a little bit different. Instead of multiplying, I need to do some division here. And then my unit is moles. I figured out how many moles I had of Skittles. And it's going to turn out to be a fraction of a mole. This number is not as big as Avogadro's number. So I don't have a whole mole. I have a fraction or a portion of a mole for this answer here. So your homework, which is due on Thursday, goes along with this. You can wait until after tomorrow's video lecture to start that homework if you'd like. Most of you are going to have no problem with it though. And again, you could probably get it done in about 10, 15 minutes maybe. So not too bad again. Keep an eye out on Skyward for those changes to the grades. Still be looking at the Google Classroom for announcements there. We've got some things in the works for graduation for the seniors, so keep your ears open, ears to the ground for that kind of news too. I will see you again for tomorrow's video lecture and for office hours today. Have a good one.